So today we're going to continue our discussions and applications of differentiation. We're actually going to talk about the mean value theorem, where mean kind of means average. And again, we're going to start with an idea here before we get to practices. Let's pretend we have a function, point A and point B, and I have them shown here on this graph. And you can tell this is an increasing function from A to B, and the average rate of change shown here is the purple line. It is a secant line between 2 points. And if I was to draw any function, and again, remember a function passes the vertical line test. If I draw any function here, there's a function f of x between A and B. What I want you to catch here is that if you look closely between the purple line, the average rate of change, and if I was to draw in a red line on the purple line, you'll see that if I move it, there is a spot where the average rate of change is equal to the instantaneous rate of change at some point C, located in between A and B. All right. Now this has a lot of applications, especially when we start dealing with tables of data. But often, like in calculus, we want to talk about the ideas. We're going to practice them. But you can see here the average rate of change, the purple line, the red line are the same. Well, the question then becomes, well, does it have to be shaped like that function? Well, I can do almost any function I want. And there's a function, and again, its average rate of change is the same as the purple line. And it doesn't have to be like that. I can make it go like that, and now C is moved. C is now right here. And also the part this time to catch, if I copy my average rate of change line and I paste in a new one, you're going to notice that this time it's not just in one spot. I'm going to have to label C1 and C2. So what we're talking about here is a theorem where the instantaneous rate of change, right here, is equal to the average rate of change in between the points. And that, with our ideas of differentiation, is pretty easy to comprehend. We can start by defining the slope, or the average rate of change between A and B. That's simply rise, change in y, over the front. That is the average rate of change. And we know how to find the instantaneous rate of change now. If this function is f of x, the instantaneous rate of change at point C is simply the derivative of the function located at position C. And we are saying that these two functions are, or these two are equal. And this is the average rate of change for the two. So the instantaneous is equal to the average rate of change. This is the mean value theorem. Now, we talked about this and we showed a function, and you notice this function had a couple of properties right away. In this case, it was always continuous. So it comes down to the question, where doesn't this work? We always have rules that go with these functions. So we've just said, well, mean value theorem is the instantaneous rate of change being equal to the average rate of change. All right? And we know that, so we take a look at this graph and we think to ourselves, well, here's a graph. If I draw in the average rate of change, is it always going to be equal to that? And the answer is no, it doesn't have to be. I can draw a function right now that won't work. That piecewise function does not work. And you'll notice it is defined at A, it is defined at B. There is an average rate of change between the values, but you'll notice at the in-between point, there is no point, no derivative on this black function that matches the purple line. So a function can't have a discontinuity. It has to be continuous in between the points. And often I have students at this point, when we start talking about this, say, well, what about if A and B are the same? Well, let's move that down, and we're going to move f of B down. So what if I move f of B down, so f of B equals f of A, and I put point B over here? Well, if I do that, the average rate of change is 0. The slope between these two lines is going to be 0. Now, if I draw this line, every point, the black line on top of purple, every point between A and B has the instantaneous rate of change and the average rate of change are the same. The derivative of the black line and the slope of the purple line are the same. And if I draw a function like this, it still passes. Right there is point C, and we know that is a point where the derivative is 0. So now we know it has to be continuous between A and B, but now, my favorite type of curve, what happens if I do this type of curve? You'll notice that it is increasing from A to this point in the middle, which I'll call D instead of C, because you're going to notice here, the instantaneous rate of change on all of these is positive. From D to B, the instantaneous rate of change on the function is negative. But this function is not differentiable at point D. F prime of D does not exist. And thus, the mean value theorem doesn't happen here. You can't. There is not a spot where this curve is 0. So now we've come all the way through and we've set some rules. We've talked about the mean value theorem is the instantaneous rate of change being equal to the average rate of change when the function is continuous and differentiable. So now we can write some rules. Mean value theorem, which often is done MVT, is when the instantaneous rate of change is equal to the average rate of change on a function where f of x, the function, is continuous on A to B and is differentiable on A to B, not including A and B, because it can be a function in between, because the functions I've drawn weren't differentiable on the endpoints. And we can organize this any way we want. And this is going to allow us to see, when we just know endpoints, to know that what's happening in between the curve about instantaneous rate of change. Again, we want to apply this to some methods. So let's use a function, f of x equals x cubed minus x. And we can quickly graph this, and I'm just going to use my calculator and copy the graph down. And we're going to do it on an interval 0 to 2. And this is a nice function because it's a polynomial. So we know it's continuous, we know it's differentiable, we don't have to waste time. It passes those two conditions immediately. And we know it's 0 at 0, f of 0, 0. And if I plug in 2, I get 6. And I take the curve kind of quickly from my graph here and just kind of, whoops, there we go, 1, 2, and 0. I love moving dots. So there's our function, and it goes through that. And again, the average rate of change, and I'm going to put the purple line here, has to equal the instantaneous rate of change. Now, hopefully, if I did my graph well, you're going to see, yeah, I'm pretty close. We probably can guess the point, but we're going to actually go through the calculations. First of all, we know that f prime of c equals f of b minus f of a of b minus a. If I plug this in, first of all, f prime of x, using the power rule, is 3x squared minus 1. So if I'm going to substitute c in here, f prime of c, it just changes c, x to c. So on the left side here, I have 3c squared minus 1 equals f of b. Well, I'll plug the values in. So we're going to use 2, b is 2, and a is 0. So I plug in 2 into the function, and I get 2 cubed minus 2 minus 0 cubed minus 0, f of b minus f of a, over 2 minus 0. And over here I get 6 minus 0 over 2, which is 3. And if I look here now, I can plug in the value and add 1, and I get 3c squared equals 4. Divide by 3 on both sides. C squared is 4/3. And take the derivative, or the square root, and I get c equals plus or minus square root of 4/3 is 2 over the square root of 3. Now, before I rationalize or anything, one thing we got to catch right away. My interval is 0 to 2. Negative is not in my interval, so I'm going to cross it out. I'll multiply by the square root of 3 on top and bottom. And I know that at the value of 2 times the square root of 3 over 3, the rate of change for that function on the interval 0 to 2, the instantaneous rate of change of that function is the same as the average rate of change from 0 to 2. So the instantaneous at 2 times square root of 3 over 3 is the same as the average from 0 to 2. Again, this is the mean value theorem. Catch the next video, which shows more examples. And again, the big thing is, remember, it's instantaneous rate of change is equal to the average rate of change when the function is continuous on the closed interval and differentiable on the open interval. Keep practicing.